And I'm happy to invite Professor Sharon Gannot from the Faculty of Engineering, Bar-Ilan University, that will talk about Lipvoicer, generating speech from silent video guided by lip reading.
Hello, my name is Sharon. Thank you very much for the invitation and for the introduction. I will talk about this Lipvoicer, which is a new work that we did, all of the people that you can see here. And we are interested in producing sound from a silent video. So we have a silent video. It can be an old movie, or it can be an old silent movie, or it can be some very noisy video that we cannot hear, and we would like to produce the sound out of it. It's actually my first zero microphone speech processing algorithm, so I'm proud of it, and hopefully you will enjoy this as well. This is part of a project that was just ended, the European Union project, Horizon, with this nice robot called Ari, and it has eyes and a lot of cameras, a lot of microphones, but for this project, for this specific problem, we don't use the microphones. So in order to do this, we need to produce a sound which is, first of all, intelligible, so something that everyone will understand. It should be very well synchronized with the lips, otherwise it looks weird, and to sound very natural, and also should align with the characteristics of the speaker himself. So like age and gender, we want to produce a sound which will look like the person, which will we could hear it as being uttered by the person that we are looking at. So this is the Lipvoicer that was recently published in ICLR. We use a generative model for this. This is the main idea. The generative model that we use is something which is very exciting in the literature or in the domain in general in the recent years, called diffusion models. But we assist it by ASR system and by lip reading system, as I will explain soon. So in again, very, very brief introduction to diffusion model. So diffusion model is gradually adding noise to a clean, in that case, image, until it becomes just pure noise. And what we want to do is to learn how to go back. So this is in general what we do. So while training, we give the system the clean image, and we end up with noise, but in test time, we have only noise, and we would like to produce, again, the clean image. Of course, we will need some assistance, which I will discuss in a few seconds. So adding the noise, we do it with a Markovian process, so we can know quite easily how to do this, how to add noise, or how to go forward from the clean signal towards noisier and noisier with small steps. We have to do this in small steps. But the problem is that we cannot go back easily. Going back, we want to go from XT, like one of the steps, towards X0, which is the beginning, the clean image or the clean signal in our case. And in order to do this, we need to know the backward probability, xt minus 1 to xt, until we go back to x0. This is unfortunately intractable problem, and we resort to neural network that will learn how to do this perfectly. So the neural network has a set of parameters, theta, and I don't have time to get into all the details, but in general, we have to optimize this noise process, epsilon theta, that will resemble the noise that we added in order to reduce it from the noisy image back towards the clean one. So this one is the neural network that will learn how to go back. So this is our system. So the system comprises several blocks. We have a video. Out of the video, we extract the lip area only. So since this is where the speech is uttered, and we take one of the images in order to have some idea on the person that is speaking. And the backbone is this smell generation block, which I will explain later, but this smell generation block is responsible to produce smell spectrogram of the speech signal, which we will use eventually in order to produce the sound. This is an iterative process that is done here by the diffusion model, but it is assisted also by a lip reader. The lip reader looks at the lips and try to find out what are the sentences that are uttered out of the lips. And while producing the sound, we want it to be as close as possible to the lip that we read. This is why we also employ an ASR system, automatic speech recognition system, and we compare them both in order to guide our diffusion process towards the correct solution. I will get into more details now. So we have all of these components. We have the MELGen that I will explain later. We have the lip reader that is applied during inference time. We have automatic speech recognition, which is applied on automatic during inference time. And from the MEL spectrogram, which is that's the spectrogram of the speech signal, we want to produce a signal that we can hear, and this we do with a neural vocoder, which is not shown in the picture before. So what is this MELGen? The MELGen is again using a backbone, which is a ready-made backbone, which is called the DiffWave. It's a system to produce sound or vocoder, and we use it in order to produce the MEL spectrogram of the speech signal. And we have the video that will guide us how to produce the correct video. So this is the MELGen. We take, as I said before, we take the lip area only, so we crop only the lip area, and from this we apply some type of TCN, which is sensitive to the time, since time evolution here is very important. So this will give an embedding of the video lips. In parallel, we have the embedding of the image, one of the images out of the video, in order to produce the correct appearance of the correct appearance of the sound that will resemble what we see in the picture. And this we do with regular ResNet. And this one, together, are conditioning the diffusion process that produces the noise that we are using in order to denoise the signal. So what we do, we take the video, we cut it into one phase, so we take one phase and embed it with this ResNet. We take the lip area, we call it VL, and we have embeddings per each frame, and then we concatenate them with the correct dimensions, and then we have something that we call the conditioning of the diffusion process. So what is the conditioning? The conditioning is actually telling us we want to add this noise that will denoise during the diffusion process, but we want to add something which will be guided or conditioned based on what we hear, or on what we see, which is this VL and IF that I mentioned before. And this is the equation that we do this. Don't want to get too much details, but this is called the video conditioning of the diffusion process. Now, something which is apparently became extremely important, we are producing a sound. The sound should resemble somehow the lip reading, but we are producing a sound actually from nothing, from noise. So if we don't take care of this, it might produce a voice that sounds very nice, but is meaningless. So this is why we would like to guide our diffusion process in order to produce a meaningful audio signal. And this we do by using the lip reader and the ASR system that I mentioned before. We do this in inference time and not in training, so it's not like conditioning that we had before, but it's something that produces or helps the process during inference time. For this, we use something that is called guidance, and in our case, it's text guidance. And the text guidance takes the noise and also produces another gradient that takes into account how much the produced audio resembles the lip reader. So they should match. If they are not matching I mean also in time, so they should be very well synchronized to the video. So if they are matching, we are good. If not, we have the gradient will be positive, and we have to correct the production or the generation of this noise. So this is in general. We take the video, we cut the lip area, we cut an image, we start with noise, conditioning on these two signals, and eventually by this guidance we produce the sound. We applied the algorithm to two well-known data sets. The first one, LRS2, is British one with British accent, you will hear it. LRS3 is also English, but with general accents, and so also non-native ones. And it's much more, it's much larger and also more what we call in the wild. So it's recorded taken from YouTube channels and so on. So it's less controlled. We take a lip reader, which is also ready-made lip reader, that has the word error rate is quite okay, not perfect, but quite okay. And just when we produce the sound, we use the crowdsourcing, this Amazon Turk, in order to know how good the sound is. It's in most scale between 1 and 4.5. So the ground truth is almost perfect, and our system gives quite high results, which is what we call toll quality already. When we look at the produced sound, we can see that if we compare it to the competing results, which have 50 or even 100% error, our error is only 17% with the smaller data set and 21 with the highest data set, but compared with the more complicated data set, but compared to the other competing method, as you will hear soon, it is much better. So this is the sound, but I think it's better to play with directly from here. So I will play first the ground truth. So this is the video with the audio, but the algorithm does not use the audio. It's just for you for reference.
Well, it's all based on this 58-page report prepared for the European Commission.
So this is the original one. This is what we are doing.
Well, it's all based on this 58-page report prepared for the European Commission.
Okay, it's not the same voice, since I don't know the voice of the person, but still it's quite clear. Interestingly, if we do not use this ASR guidance...
It's all based on a 58-page report prepared for the European Commission.
It's gibberish, yeah, which is nice. Just as a comparison with one of the competing methods. It's quite intelligible, but it's not good. I think I have much more. You can see it on also the website. Maybe it's time to open the stage for questions. One more example you want? Okay. Let's go for a woman.
Can they improve on that score and possibly run away with the trophy?
And our algorithm.
Can they improve on that score and possibly run away with a trophy?
Wow.
And the gibberish one.
How they improve on that score and possibly run away with a trophy?
Very well synchronized. Gibberish.
Wow, so...
Okay.
Great, so it's really amazing to see it's in action, so thank you for sharing the videos. We have time for some questions from the audience.
When you trained the model, you probably took the facial characteristic from these images. What impact do they have on the voice?
Well, it should resemble somehow the appearance of the person. So you want to have an audio which, like, if it's a male voice, if it's a male, I want a male voice, and not a woman's voice, for instance. So this is it's somehow embedded inside the system. I don't know how it is doing this, but it is very good in gender.
No, I speak more about tonation, angry, scary, emotions, stuff like that.
I don't think that we are capable. We didn't train the system to do this, so I'm not sure that we can do this. If our task will be to train it for the emotional state, then we can do this. By the way, I'm working in other work also related to the robot on emotion recognition, so it might be related from audio and video together.
Thank you, amazing work.
Thank you very much, very impressive demo. Would you please tell if the voice synthesizer you used was created by your team, or you are using something like 11 Labs or stuff like this?
We took this diff wave as a backbone to produce the sound. So this is like a general vocoder that is available online. We used it twice actually. We used it as a backbone from the MEL spectrogram toward the speech, which I didn't show in the picture. And we also used it as the backbone for the diffusion process itself to produce the MEL spectrogram. But we used it, but we of course had to train it again, but we used the same backbone.
Great. So let's thank again Professor Sharon for this unreal work.